Hey, hello, everybody. Hey, we are, this is going to be a lecture on momentum and specifically collisions. And we're going to elaborate on inelastic collisions, which you will see what they are. And then there will be a separate video for elastic collisions. So here we go. All right, so you guys, a review from last week. What is momentum? What is momentum? Anybody? What is momentum?
Like the force behind something, like a moving.
Okay, we've got a force behind a moving. I like that, Geed.
The way an object is moving.
The way an object is moving, I like it. Doctor?
Something that has power?
Perhaps. So you guys, all of those are kind of dancing around the issue, okay? But you kind of have the right idea. So you guys, momentum is simply mass times velocity, okay? So that comment about something moving, okay, is definitely in there. But remember that if you have a more massive object that's moving at the same speed of a lighter object, the more massive one is going to have more momentum. So if you were to think about in your head, looking at like a couple cars like I talked about last week. So you got a small little car like an Austin Mini or one of those little tiny smart cars. If they were just going along like at a couple miles per hour, you might think about getting in front of it to try to stop it. Okay, if it was kind of rolling down a slight hill, you might get and be able to do that. But if you had a great big truck like a Ford F-150 or something, the idea of getting in front of that and trying to push it would probably not enter your mind, because the bigger car is going to have more momentum. I like to think of it as kind of the oomph, right? If you were to get knocked by someone's walking by and they kind of hit you. If that person was really light, okay, and they hit you, there wouldn't be as much what I'm going to call oomph. But if there was someone that was really big and they hit you, then there's going to be more oomph in that hit. Does that make sense? Okay. So the other thing that is important, okay, which you guys kind of talked about, and that is impulse. And impulse is force times time. Impulse is force times time. Okay, so if I push on something for a certain amount of time, I'm giving it an impulse, right? So remember that work is force times distance. Force times distance. So force is definitely related to momentum, and it is related to work. Remember, the relationship between distance and time is things like acceleration and velocity and stuff like that. Okay, so the other thing is the change in momentum, which would be like m delta v, is going to equal to force times time. So if we want to move something, if we want to change it, we're going to put a force behind it, okay, and for a certain period of time, and then it's going to change the velocity. And that also goes back to force being ma. Force is equal to mass times acceleration. All right. Conservation of momentum. Okay, you guys, what is conservation? What is conservation of momentum? Conservation of momentum. You guys, when you're thinking about conservation of momentum, I want you guys to think about conservation of energy. Conservation of energy. Can anyone tell me what conservation of energy is?
Energy cannot be created or destroyed.
Perfect. Energy cannot be created or destroyed. Then how can it go from one place to another? Okay, it's just going to get transferred. For example, what we've done for the past 3 weeks is gravitational potential energy turning into kinetic energy going back up into gravitational potential energy, that sort of stuff. So conservation of momentum, okay, is essentially momentum is neither created nor destroyed. Transferred from one object to another. Okay, now you guys, this should bring up two things that are contradictory, right? We just said that the change in momentum is equal to force times time. But here we're saying we're not changing momentum, okay? So the key here is in an isolated system, okay? So we have, you guys, we've been talking about an isolated system when it comes to energy, okay? So if you have a car that's just sitting there and it's not moving, and then all of a sudden you turn on the engine and go, it seems like we don't have that conservation of energy, but that isolated system, something can come along and push that, like the engine or wind, or something can come in and hit that, and that would be outside the system, and then we can see that change, all right? So we're gonna look at a quick example here. All right, and we talked about this last week. Okay, so you guys, we have two skaters here. All right? Now, let's say that they both have a mass of 50 kilograms and they both have an initial velocity of 0. So if their initial velocity is 0, then what is their momentum? So remember, going back to momentum is just mass times velocity. Since their velocity is 0, they have no momentum. Okay? So this system, which is just the two skaters, okay, their momentum is 0 in the beginning, okay, so which means after any sort of interaction, as long as it stays within the system, their momentum is going to be 0. So if they push off each other, right? So they push off each other. Now we're going to have force times time going that way. And let's say that they're going 5 meters per second. So it appears, and it is true, that the momentum of the blue skater is 50 times 5, which is 250 kilogram meters per second. Okay, so the momentum is 250. That is not 0. So how do we know that the overall system is going to add up to 0 for its momentum? Well, the other skater, if it has the same mass, you might imagine that it is going to go backwards at the same speed, and it does. So the only way that is going to go backwards is going to have a velocity of -5, and -5 times 50 is -250. And therefore, the total momentum is 0. Okay, so conservation of momentum does in fact take place. Okay, so now if we were to just talk about this blue skater, okay, and it's got 0 momentum, and we say that this blue skater is the entire system, okay, and now the purple skater pushes off, and they push off one another. Now it's no longer an isolated system, because the purple skater added to this system from the outside. Okay, so that's why we can get this change in momentum, increasing its speed. So here is, you guys, here is something that is really sort of weird here. What if this was just a wall, okay? What if this was just a wall, and now we have this blue skater. This blue skater is going to push off of the wall, okay? So now it's going to have a momentum of 250 this way. And we are going to include the wall. We're going to include the wall in our system, okay? So what is the momentum? What is the momentum of the wall? If the momentum before is 0, the momentum of the blue skater is positive 250, and now they're pushing off a wall. What is going to be the momentum of the wall? And the answer, just like the purple skater, it's going to be negative 250. Okay, so this wall is going to move back with a certain velocity. But what is that velocity? You guys, what is the velocity, or what is the mass of the wall? Well, the wall is attached to the ground, and the ground is obviously part of the earth. So it's actually the earth that would go backwards this way. But because the mass of the earth is so big, 6 times 10 to the 24th, that'd be like 6 with 24 zeros, past it. So it's an enormous thing. So we don't really see it moving. Okay. So in the same way, you guys, if we drop this pen, why does it go down? Why does it go down when I drop this pen?
Gravity.
The gravity is pulling the pen towards the earth. But at the same time, the earth is being pulled up to the pen. The earth is being pulled up to the pen. There's an attraction of this pen that's bringing up the earth. How come we don't notice that the earth is coming up to the pen? Because this pen, compared to the mass of the earth, is so little that we only really see this move, okay? So it seems kind of bizarre that we have that, but it has to do with the fact that the earth is so big. All right. Now, you guys, if we have these two objects and they separate, and now we turn that, visualize that as a movie, okay, or a video, and we have these two skaters and they push off each other and go this way, and now we do that in reverse, and now they're going to come together, and that is going to be a collision. That is going to be a collision, okay, and that's what we're going to talk about. That is what we're going to talk about next, right? All right, so there are you guys, there are three types. There are 3 types of collisions. 3 types of collisions, okay? One is elastic, and the other one is inelastic. All right, so I thought you said that there were 3, okay? And there are, but we're going to add something. We're going to say perfectly elastic and perfectly inelastic. Okay. So first of all, you guys, what does elastic mean? What does elastic mean? Anyone want to take a guess as to what elastic means? You guys, I have a ball. I've got a ball right here, okay? And I'm going to drop it. Was that an elastic collision or an inelastic collision? Why would you say it's an elastic collision? Because it bounced, right? So to identify an elastic collision, we're going to say when it hits something and it bounces. When it hits and bounces, okay, that is going to be an elastic collision, an elastic collision. Okay, you guys, I have another ball, okay? I've got another ball right here. And when I drop this ball, watch what happens. Let me try that again so you guys can see it. I'm going to take this ball. Now, what kind of collision is this? And it obviously, it's going to be an inelastic collision. So what happens? What happens in an elastic collision after it hits? Okay, it doesn't hit and stick. Sorry, it does. It hits and then it sticks together. It hits and it sticks together. Okay? Now, when we add this word perfectly, okay, when it hits and bounces without losing kinetic energy or momentum, okay? So you have a perfectly elastic collision if it hits and sticks and it doesn't lose any kinetic energy and it doesn't lose any momentum. That's perfectly elastic. Now, you guys, perfectly inelastic is when it sticks and it loses kinetic energy, but still keeps its momentum. Okay, so perfectly elastic, perfectly inelastic. Okay, hits and bounces without losing any kinetic energy. So let's take a look at this first one here. We've got this rubber ball here and we drop it. You guys, was that perfectly elastic? If I do this, is that perfectly elastic?
No.
Why not?
Because it didn't bounce.
It did not bounce up. It did not bounce up to the same height. That is the key to the fact that it's not perfectly elastic, okay? So in the same way, if it's not perfectly elastic, then there's some there's some inelastic properties to it. Okay, so our third type of collision is really just a combination. We're partially elastic and partially inelastic. Okay, so we'll say it's a combination collision, and we can say partially elastic and therefore partially inelastic. Inelastic. All right. So, you guys, is there ever anything that is perfectly elastic? Is there any type of collision that's perfectly elastic? In your experience, would you say that there's anything that's ever perfect? Probably not, right? So when I drop this, for example, Can you guys hear that bounce? If you can hear that bounce, then some of that energy that was contained in the ball was being lost, and you get that by sound. Also, the ball is going to squish, and if we squish this ball up and down a bunch of times, we would see its temperature rise, okay? So we know that it's going to lose some energy here, okay, even if it is mostly elastic, okay? And that's kind of the same thing when we talk about mechanical energy. Mechanical energy is just the kinetic plus the potential. And what we talked about for the past 3 weeks is the conservation of mechanical energy. And what we do when we talk about conservation of mechanical energy, we are ignoring the thermal energy, okay? But that makes it a lot easier. So if we start with 100 joules of mechanical energy, and at the end we only have 90, okay? Well, we know we should have 100. So the difference, that 10 from 100 to 90 is 10. We would know that that had to have been lost to thermal energy. So by knowing what that perfect score is, when we don't see it perfect, the difference we can account for with other things like thermal energy, okay? All right, so those are our 3 types. Now, we are now going to talk about the mathematics. You guys, we're going to talk about the mathematics of an inelastic collision. The mathematics of an inelastic collision. Okay, so let's see. We can go right here. Okay, so we are going to have M1, V1 initial, okay? So we have, let's say, 2 balls, okay? So we're going to have ball 1 and ball 2, okay? So this is mass 1, sorry, I'm going to make this mass 2, and we'll make this mass 1, okay? So let's say this is 1 kilogram and 1 kilogram. We're going to use this. We're going to use this as an example. Okay. So remember, mass times velocity. This is just the initial velocity of the first ball. Okay. And now we're going to add to that M2 V2 initial. M2 V2 initial. That's the momentum of the second ball, right? So now, if they hit and stick to each other, what is their mass? If they hit and stick, what is their new mass? And it's M1 plus M2. Okay? Now, if they hit and stick, what is their velocity? Well, it doesn't matter what their velocity is. The velocity is the same because they're now stuck together. So now we can just say V final. We can now say V final. Okay, so let's do an example with this one right here. So let's say this is our before, and we're going to say that the initial velocity, we're going to have the initial velocity of the green ball is 0, and we're going to have the initial velocity of the first ball, let's say, is 6 meters per second. Okay, and again, it's 1 kilogram. Okay, so now, if we now do after, okay, so now we have these 2 balls that are now stuck together, and we're looking for their final velocity. Okay, and we'll put our before and after down here. Okay, you guys, now we're just going to plug in these numbers up here. So we're going to say 1 times 6 plus 1 times 0. Okay, so you guys, just thinking about that, if you've got the black ball hitting the green ball and they're sticking, what do you think their final velocity is? What do you think their final velocity is after they hit and stick? 3 meters per second is correct. Why did you say that?
Because the masses are doubled.
So since the mass doubled, the velocity got cut in half. Since the mass doubled, the velocity got cut in half. Okay. Now, you guys, this is conservation of momentum. Okay. The momentum we have before is 6, right? Because 1 times 6 plus 1 times 0 is going to be 6. Our total momentum before is 6. And now afterwards, we're going to have a mass of 2 times our velocity final. 6 divided by 2 is going to be 3. 6 divided by 2 is going to be 3. Okay? Now, you guys, if they're the same mass, if the two objects are the same mass, then their velocity is just going to get cut in half. Their velocity is going to just get cut in half. All right? You guys, what if we change this mass to 2 kilograms? You guys, what do you suppose the velocity after they hit is now? If it's still 6 and 0, but now we've got twice the mass, so now we're going to have a mass of not 2 but 3. What is the final velocity of the two balls? It's going to be 2 meters per second. Because we have 3 times the mass, we're going to have 1/3 of the velocity. Make sense? All right. So you guys, let's talk about this going back into 1 kilogram. 1 kilogram. But now we're going to say the initial velocity of the green ball is -6. And the velocity of the black ball is +6. And now they're going to hit and stick. What is their final velocity going to be? It's going to be 0, right? So they're just going to hit and then boom, stop, because they hit and stick. So our overall momentum, okay, our overall momentum would be 1 times 6 plus 1 times -6, which would add up to 0. So now our mass is going to be 2 here, but it doesn't really matter because 0 divided by 2 is just 0. Okay? So if they have different masses, let's say that this is going to be 2. Okay? Now, if this is going 2 kilograms at -6, and this is 1 kilogram going at +6, what is their overall average velocity after the case? Okay, so now we can put in 1 times 6 plus 2 times -6. Okay, now 6 plus -12 is -6, right? But now we have twice the mass, so our velocity, our final velocity here would be -3 meters per second. -3 meters per second. All right, so you guys, that right there is inelastic collisions. Okay, so we're going to stop this lecture right here, and then we're going to see the new lecture on elastic collisions. So we'll start and stop, and we'll see you in a minute.